I'm going to, at least for now, take the sign-in sheet down and try hard to remember to put it up again a little bit later. Okay. Oh, come on. It doesn't like my finger this morning. I feel like that one's slower to respond to me when I try to switch it. Here we go. Okay. So solving the initial value problem just means I've got two steps to do. My first step is to look at that derivative or that differential equation. Again, it's a differential equation because I've got a derivative and an equal sign. That's it. So I need to find the antiderivative, and the initial value problem part is what tells me I need to actually solve for the constant c when I'm done. So if I'm thinking about this antiderivative, if you don't have antiderivatives memorized yet, it's okay. It's only week 2, but it's going to be really important that we've got the basic antiderivatives memorized quickly. There's a chart on my version of the book. It's on page 345. But there's a chart of antiderivatives that you should memorize. E to the ax is one of those that's in the chart. So if I go to find this antiderivative, the antiderivative of e to a number times x is going to look like e to that number times x divided by 3. And it's kind of like we're undoing that chain rule piece where when we were doing derivatives, we would multiply by that constant, and we're finding the antiderivative, we're going to divide by it. The antiderivative of -5 is just -5x. And when we have found that antiderivative, we're going to remember to add in a generic constant. That's sometimes what we refer to as a general solution. And then when I go ahead and solve that initial value problem, that's going to give us our particular solution. So this notation tells me that when x is 0, the y value should be 4/3. By the way, we call it an initial condition regardless of whether the x value in there is 0. So I could have said y of 1 is equal to 4/3, and we would still call that the initial condition. Plugging that in, I'm going to exchange my y value and plug in a 4/3. And everywhere that I've got an x, I'm going to plug in 0. And doing a little bit of quick algebra here. 3 times 0 is 0, which then the e to the 0 is 1. So that means I'm looking at 1/3 minus 0 plus that constant has to equal 4/3. So I kept our numbers pretty nice here. Gave us a common denominator already. So if I were to subtract 1/3 from both sides, I would have 3/3 or just 1. Once I know that c is equal to 1, my final answer is going to look like plugging that 1 in back to the equation. So my final answer, if I want full credit, is going to need to look like e to the 3x minus 5x plus 1. Questions about this before I move on? Would anyone like another one to practice before I move on? Yeah, I saw some yeses. Sure. So solving this equation, I'm subtracting 1/3 from both sides. And 4/3 minus 1/3 gave me 3/3. Yeah, which I just simplified to 1. Shall we dive into this? Okay. Kind of similar to what happens with our e to a constant times x. when we're finding antiderivatives and we just have something simple like a constant times x somewhere inside of the function, usually that's an indication that we're going to undo that chain rule by dividing by the constant. So when I look at sine of t, I'm asking myself, whose derivative is equal to sine? And the answer to that is almost cosine, but it's negative cosine. So the antiderivative of a positive sign becomes a negative cosine. You all will get tired of hearing me say this. Calculus cannot change the argument of a trig function. Whether you're taking derivatives or integrals, what's inside of a trig function can't change. Only trig identities can make that change. But because I have that 2t, I'm sort of going to undo that chain rule by dividing by 2. For my next part, I've got a negative 3 cosine of 3t. And I'm asking myself whose derivative is equal to cosine. So I'm going to have negative 3 sine of 3t. And then I'm going to do that same thing and divide by 3 to sort of undo the chain rule piece. And then I'm setting that, we're going to add a plus c. Certainly these 3's I can cancel out, which is kind of nice. So if I wanted to clean this up just a little bit, or even just think about rewriting it a little bit, I would have negative 1/2 cosine of 2t minus sine of 3t plus a constant. Moving to deal with our initial condition. Our initial condition here says that when t equals pi, w should equal 2. So I'm going to replace my w with a 2, and everywhere I've got a t, I'm going to plug in pi. So a question came up about, do we have to simplify the cosine of 2 pi and the sine of 3 pi? I'm going to say that you probably don't have to in terms of like getting your points. I think we should, because life is going to be a lot easier if we do. So quick, just trig refresher. Lots of different ways to go about memorizing some nice trig angles. One of my favorites, because you should probably know what the graphs of sine and cosine look like anyway, is to just think about a quick sketch of sine of x and cosine of x. So if this is just a regular old y equals sine of x, and the period is 2 pi, then pi is right in the middle. I kind of didn't leave myself enough room on the paper because I just realized we need to know what sine of 3 pi is. So if I kept going, I'll just squeeze it in a little bit there. This is going to be back to a value of 0 at 3 pi. So that sine of 3 pi is equal to 0. Cosine of 2 pi. So cosine starts up here with a value of 1. At pi, it's got a value of -1. And by 2 pi, we are back up to a value of 1. So cosine of 2 pi is equal to 1. So after we do that, I'm looking at 2 is equal to -1/2 plus c. And then you have options on how to deal with that. But if I add 1/2 to both sides, I could either think about that as a 2.5, or I could think about that as 5/2. Both of those are totally fine. I tend to prefer fractions over decimals, but not a big deal if decimals are better for you. So looping back around to make sure that I get to a final answer, I'm going to write that w of t is equal to negative 1/2 cosine 2t minus sine of 3t plus 5/2. And that whole thing is my final answer. By the way, I took that 5x cubed, and I'm going to choose to rewrite that as just this last piece as 5 times x to the negative 3. That way we can use our, if I've got a number times x raised to a number, I get to add 1 to the exponent, divide by the new exponent. So here I'd have 3x, add 1 to the exponent, divide by the new exponent. You can cancel the 3's or not. Add 1 to the exponent, divide by the new exponent. And here, if I use this version of it, I'm going to add 1 to the exponent and get a negative 2, and then divide by a negative 2, plus a constant. Lots of different ways we can rewrite that. We could simplify that to say something like that, perhaps, but it's not the only option. Okay, so for the second one, my hint was to rewrite first. And I know I gave us fraction exponents. Fractions are your friend. So if I look at that square root of x piece, that part in particular, I'm going to want to rewrite as x to the 1/2 power. Now, the other thing that I recommend that we do in terms of rewriting it, I'm going to do this in 2 steps. You could do this in 1 step. I'm not finding that antiderivative yet, but I'm going to split this apart as 2 fractions and say that's 3x to the 4th over 2x minus x to the 1/2 over 2x. That intermediate step, you don't necessarily have to write. You could go straight to, I know that x to the 4th over x is going to leave me with x to the 3rd. And I know that x to the negative 1/2 over x is going to leave me with x to the negative 1/2. Because essentially I'll have 1/2 minus 1 in terms of working with those exponents. Now everything is a number times x raised to a power, and we're just going to apply our power rule. So add 1 to the exponent. That'll be to the 4th. And then when I divide by that new exponent, I'm going to have a 2 times a 4 on the bottom. I'm going to write that as 8. Here, I'll write this out because they're fractions. If I add 1 to the exponent, I'm going to have x to the 1/2. And when I divide by that new exponent, the 1/2s will conveniently cancel out for us. And then because I want all my points, I'm going to write plus c. Dun, dun, dun. In the scheme of all of the techniques that we are going to have for finding antiderivatives, I think that this kind of algebra stuff is on the more straightforward end of the spectrum, and we're going to do things that are more complicated. So spending some time to practice this is good. Question, yeah. So I could have left this as 3/2 divided by 4, and that'd be okay. But fun with fractions, if I have 3/2 divided by 4, secretly that 4 is a 4 over 1. So that's equivalent to saying 3/2 times 1/4, or 3/8. Did we talk about the last one? Okay. So I am again looking at this, and I'm just going to think for each part, like, whose derivative is that? So 2/t is the one exception where I wouldn't rewrite that as t to the -1. But let's pretend for a second that we did. So if I had rewritten that to be 2t to the -1, not really anything I can do to those other pieces, so I'll just leave them alone. If I tried to follow the power rule from there, what do I get when I add 1 to the exponent? So I'd have like 2t to the 0 divided by 0. Dividing by 0, not a thing we get to do. So if you accidentally do that and you get to the point where you're dividing by 0, something should go off in your head and go, oh, wait, that's the weird one. That's actually natural log. Because instead, I probably ought to be looking at that and saying, whose derivative is this? And the derivative of 1 over x, sorry, whose derivative is equal to 1 over x? Natural log, ln of x. Woohoo! So that antiderivative, the function whose derivative is 2/t, is 2 natural log of t. Now there's a catch, and I know that you all talked about this in lecture. The catch here is that what sorts of values am I allowed to plug in to a natural log? Yeah, can I plug in 0? So just positives. I can only plug positive values in. The issue is that the function 2/t has a domain that includes negative numbers and positive numbers, just not 0. So when we find the antiderivative, in order to make the domains match, what we do is we put an absolute value on the t. And now the domain for natural log of t matches the domain for 1/t. It's a subtlety, but it is the kind of thing that's going to maybe lose you a point. So it's worth just practicing putting the absolute value bars on there. My next piece, 5e to the 7t. 5's coming along for the ride. I'm going to have that e to the 7t. And then because I have a 7 times t, I'm going to sort of undo that chain rule piece again by dividing by 7. The antiderivative of 12 is 12t. And then I'm going to want to add a plus c.